Thank you, York. All right, this afternoon I'd like to discuss the current state of second law research. And I'd like to give a brief introduction, starting with the discussion of energy, and then moving on to a brief introduction to the second law and why one should consider the possibility that it may be violable sometime in the near future. And then finally discuss some of the breadth and depth of the subject. Quite literally, energy does make the world go round. Rotationally, kinetically, chemically, economically, geopolitically, militarily, almost everything you see in the world is connected with energy because energy is the currency of change. Without it, nothing happens. The current worldwide use of energy is roughly about 15 terawatts. Now, to put that into perspective, it's equivalent roughly to the energy every 5 seconds. The power use is equal to that energy of roughly a World War II nuclear bomb going off. And by 2025, roughly about 50% more energy will be required to run civilization. And by a modest and conservative estimate, roughly 20% of the world's economy is devoted to energy, to discovery, extraction, transportation, use, and in the case of the Gulf, remediation from the extraction process. In terms of energy use in general, about 85% of it is fossil fuel, coal, natural gas, and oil. The rest, nuclear and renewables, make up a smaller fraction. By sector, roughly a quarter is used in residential, a quarter in industry, a quarter in commercial, a quarter in transport. And in terms of world consumption as of 2002, North America, primarily the United States, makes up roughly about 27% of the world's energy use. The rest is in Eastern and Western Europe for the first half. Most of the world survives on roughly the other half of this. But if you'll notice, China and India, which make up roughly a third of the world's population by themselves, only make up a small fraction now, but as they emerge into first world economies, they will begin to eat up a greater share of this. And of course, there are finite supplies. Current estimates are that oil has roughly about 40 years left, gas about 70, and coal about 250. This is the famous Huber curve, which was predicted back in the 1950s, predicting the oil production in the United States versus year. The prediction was that it would peak roughly in about 1970, and indeed it did. The United States now imports roughly about 60% of its oil. The Huber curve for coal would follow something along these lines. We're here right now coming up the curve. It should peak around 2100 or so, and then tail off from there. But if we put all of this CO2 into the atmosphere, I think we all know we'll burn down the planet. So the inconvenient truth and consequences of this. Obviously, climate and environmental change, pollution, global warming, ecosystem destruction, and many biologists believe we are in the middle or the beginning of a mass extinction, which will be comparable to the previous 5 in the last half a billion years. The Ordovician, the Devonian, the Permian 250 million years ago, the Great Dying, the Jurassic, Triassic, and the Cretaceous Tertiary, which was 65 million years ago. This mass extinction, though, is being overseen by us through all of these terms above. And obviously, there are insufficient supplies of energy. We have economic instability as a result of this, fuel and food shortages, social unrest, and judging from some of the recent activities of the United States, can also lead to military interventions. The alternatives to fossil fuels and nuclear are numerous. We have solar, thermal, photovoltaic, hydro, wind, tidal, and geothermal. But all of these have their disadvantages in terms of capital costs, scale size, efficiency, renewability, unit cost, and so on, such that it's unlikely that any of them, or even all of them, will be able to fill the energy vacuum that will exist in the near future. So what would be an ideal energy source? If you were to just write down a few characteristics of something you might consider to be an ideal energy source, it should be one that is ubiquitous, found everywhere. It should have a high power density. Now, you may think solar power is good, but it does not have a high power density. Roughly, if you put solar panels out and collect all the sunlight coming from the sky on a square meter of surface area at normal incidence, you'll get roughly a kilowatt of solar power coming in, of which you might be able to glean 20% of that. And you won't get any more than that. So you'll never be able to get more than about, let's say, 200 watts per square meter. And that's all you'll be able to get. So to power a city, you need acres or square miles of such solar panels in order to handle it. So high power density is something that should not be ignored. It is in a sense the concentration of energy. And so you'd want a high concentration of power and energy coming out of your ideal source. It should be green and non-polluting, plentiful and inexhaustible. So what might this mean? Well, the most ubiquitous energy source available, I should not say available, around us is thermal energy. The air molecules in this room, the nitrogen and oxygen molecules, are moving roughly about 400 meters per second, roughly the speed of sound, constantly. We don't feel it because they're small and their average momenta, when they bounce off of us, add to zero, so we really don't notice it. A glass of water, for instance, the one that are sitting on your desk right now, a full glass of water in terms of thermal energy has roughly the thermal energy equivalent of roughly about 1/10 of a kilogram of TNT. And that includes everything else in this room, the ceiling tiles, the rugs on the floor, the tables, our flesh, everything is loaded with energy. But it's in a form that can't be used easily. The atmosphere, ocean, and crust. If you were to add up all the thermal energy in these three, in the upper crust and the atmosphere and ocean, you'd have roughly 10,000 times the amount of energy in all the fossil fuel reserves that are known. And these are constantly being replenished by solar and radioactivity in the crust. It is essentially, it is plentiful and in principle inexhaustible if you can get at it. So thermal energy has all of the characteristics in principle that you would want out of an energy source that's ubiquitous, high power density, plentiful, inexhaustible, recyclable, but not really, because of the second law of thermodynamics, which is probably the most depressing law in nature. There are 4 laws of thermodynamics. The first is actually called the zeroth because it was thought of afterwards, and so since they already named the first, second, and third, they had to go back and throw in another one. If another law is found, it would be called the negative first, probably. But the zeroth and third law, which the zeroth basically tells you thermometers exist. You can measure equilibrium. You can measure temperature. It's basically a definition. And also the third law is basically a throwaway as well. It talks about fiduciary entropies. But the first and second laws, they are the heart and they are the soul of thermodynamics. They are the flesh and the blood. This tells you, as mentioned previously, it's a bookkeeping technique in a sense. But the second law tells you what you can and cannot do. And we understand this in our bones. We have lots of colloquial statements about the second law. Heat flows from hot to cold, not the other way around. Masses fill the space available to them. Murphy's laws. Anything can go wrong at will. Situations tend to progress from bad to worse. And of course, the one you learned in kindergarten, which is drilled into you for your whole life. Perpetual motion machines are impossible. And this is probably the most damning of them. The technical formulations of the second law are also numerous. The one that I prefer is the Kelvin-Planck one, which goes back 150 years. No device operating in a cycle can produce the sole effect of the extraction of a quantity of heat from a reservoir and the performance of an equal quantity of work, which basically says you can't take heat and turn it solely into work with nothing else happening. You can't take that disorganized molecular motion and reorganize it completely. Clausius heat basically is one that says heat goes from hot to cold, not the other way around. Perpetual motion machines are impossible. Perfect refrigerators are impossible. Perfect heat engines are impossible. All natural processes are irreversible. The entropy of the universe constantly increases or at least never decreases. We're all going to die. Okay, so the second law basically says that. The universe tends toward greater disorder. Energy runs down. The second law takes a tax on every single thermodynamic process in the universe. It takes away some of that energy which you can never recover. In the book Vlada Kapik and I wrote several years ago, we actually found 21 different formulations of the second law of thermodynamics, some of which don't even seem to agree with each other, but there are many different forms of it. And as Clifford Truesdale once noted, the famous historian of science, every physicist knows exactly what the first and second law of thermodynamics are. The only problem is no two physicists agree on what they are. There is what I would call the second law mystique. There is a cocoon, an intellectual cocoon around the second law that makes it almost impossible to discuss in a rational way in the scientific community. And the most famous quote about it is by Arthur Eddington, who happened to have been a scientist of equal caliber and stature to Albert Einstein in the early 20th century. And for those of you in the back, the law that entropy increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, well, so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. And this is the general tenor of remarks regarding the second law. It is an unquestioned axiom. But one of the things that is often forgotten is that the laws of nature are not set in stone. They are discovered. And on purely epistemological grounds, they cannot ever be fully proven. They can only be verified. And you can go no farther, if you wish, than to David Hume's problem of induction to show that to be the case. Laws of nature are true because they are found to be true. If you could prove them, they would be theorems of deeper axioms. So, and furthermore, laws must be updated on a regular basis and made more precise. So let's take an example. The laws of gravity. Back about 300 BC, Aristotle said, things fall. That's gravity. Why? Because they fall to where they like to be, which is the ground. And to show how persuasive that argument is, it held for 1,500 years. So he was a very smart guy. Newton came along and developed his basic theory of gravity, universal theory of gravity, which was updated a couple hundred years later by Einstein. But even within 20, 30 years after Einstein discovered his theory of gravity, the general theory of relativity, it was already known that it was wrong because it didn't incorporate quantum mechanics. And even to this day, better part of a century later, we do not have a viable theory of quantum gravity. So even if something as simple as gravity constantly needs to be revised and updated on a regular basis. Conservation of energy is another one. Until about 1800, there were only two kinds of energy which were known, kinetic and potential. The energy of motion, the energy of energy in the arrangement of material, for instance, gravitational potential energy. By 1850, it was discovered that heat, random molecular motion, was another kind of energy. By 1905, rest mass energy was discovered. 1940, zero-point energy was recognized well. 1970s, false vacuum energy, from perhaps which the universe came from, was discovered. 1998, dark energy. Whenever a new form of a means by which to change the universe is discovered, they simply invent, a new kind of energy is created, and the first law of thermodynamics is updated. Now, the history of the second law can really be traced back almost 200 years now to Sadi Carnot in heat engine efficiencies. But by roughly 1910, no further statements of the second law really were being developed. It was considered pretty much set in stone almost a full century ago. Since that time, we've had special relativity, we've had quantum mechanics, chaos theory, updates in cosmology. Virtually any basic law or statement in physics had to have been updated in the last century, but not the second law. My form of the second law goes back 150 years or more. So in general, laws become rules of thumb. Things like the ideal gas law are known not to be true. There are no perfect ideal gases, but it's close enough that we can use it. We have Charles's law, Gay-Lussac's, Raoult's law. All of these laws are updated and considered approximations. Is it possible that the second law itself, which was last updated 100 years ago, roughly, is also an approximation? Good for almost everything we deal with, and good for everything we do deal with, but that there might be some crimps, some imperfections in it that might be exploited. Because if you can, in principle, you can extract heat from the environment. The amount of energy in the room itself here is equal to several boxes of TNT, enough energy to run this room forever, since you can, in principle, then recycle that energy into lights, computers, projectors, food, chemical energy. So if the 21st century actually is a century when the second law is broken, then the second law will just have to have a small update. For any spontaneous process, the entropy of the universe never decreases, except when it does. So challenges to the second law. The first challenge to the second law was a thought experiment by James Clerk Maxwell himself, one of the founders of statistical mechanics, back in 1867, 140 years ago. And this demon consists of a quick-fingered creature who can operate a trapdoor. And all he does is operate this trapdoor, letting molecules through when he wants and keeping out other ones when he doesn't want them. And so you can imagine that this demon could selectively let molecules from this side of the room, this side of the partition, come through while blocking any molecules trying to come the other way. If he does so, then he creates a pressure differential, a large pressure here and a vacuum over here, in which case this piston can be pushed and do pressure volume work. When he's done with that, he opens up this door again, lets all the molecules go to the other side, creates another pressure differential, pushes the piston back, and in principle, this creature could violate the second law. It took the better part, well over 100 years to figure out what's wrong with this. And the problem with it is this demon, this creature has to think and has to remember and has to erase information. And in the process of erasing information from his register, in order to keep this process going in a cyclic way, he increases the entropy of the universe. Since that time, since James Clerk Maxwell, there was a hiatus for over 100 years before any challenges to the second law made it into the scientific literature. There was so complete an embargo on it. This embargo was broken in about 1980 by two pioneers, Jack Denier, an American, and Lindsay Gordon, a New Zealander. They snuck a couple of articles into very good refereed journals, which first raised the hint that there might be a problem with the second law, roughly about 1980. By 1990, a number of scientists had caught wind of this, and there was really quite a revolution going on. Here's a list of the modern challenges to the second law since 1980 by the research group, the institution, the country, the number of researchers in the research group, and the number of refereed publications in physics, chemistry journals that came out of these groups. On the far right is a demarker as to whether these are experimentally measurable or not. Many of them, particularly the group in the Czech Republic, were all theoretical, as were the ones by Denier. But ones by Nikolov and Keefe and the ones at the University of San Diego where I work are experimentally testable, and I'd like to focus on those. By the way, the number of challenges that have been brought into the refereed scientific literature in the last 30 years has been over 24 in over 60 articles. Just in the last 15 years, most of those appeared, and that's more than appeared in the last 150 years or 200 years combined. Of the experimentally testable challenges, the ones that were most provocative, two of them work in a low temperature regime with superconductors. Neither has real commercial viability. The ones that have been explored at the University of San Diego, 4 out of the 5 of those are in high temperature regimes or in regimes which would not be commercially available. But there is a semiconductor one that may be and which is being pursued. And the work is being supported by, partially by Hub Lab. Ed Beardsworth, you have your hand? Thank you, Ed. Okay. Here's a list of the journals in which second law challenges have appeared in the last 20 years. You'll notice many of these, recognize many of them: Physical Review Letters, American Journal of Physics, Chemical Physics. Many of the top journals in science have sponsored and accepted articles having to do with challenges to the second law. So it can no longer be said that the second law is immune from discussion. It has not been violated, though, by any experiment. And I myself will say the second law is inviolable until it isn't. Alexei Nikolov in Russia has been pursuing inhomogeneous superconducting loops. These are mesoscopic in size, roughly about a few microns in size. They are superconducting loops of aluminum. And what he does with them is tries to rectify thermal fluctuations using what's called the little Parkes effect near the transition temperature for superconductivity. He's gotten some anomalous behavior. He has not been able to directly show he's been converted into work. This work has been suspended, to my knowledge, over the last 5 years due to lack of funding in Russia. Peter Keefe, an American, has worked in this area as well, also making mesoscopic superconductors. This would be a normal conductor. This would be a magnet, and these would be magnetic field lines. If the normal conductor is brought into the region of the magnetic field and then undergoes a superconducting transition, the Meissner effect will expel the magnetic field lines out of the conductor, causing the conductor to be expelled, and during this you can do work. And so he proposes what's called a a coherent magnetocaloric engine in which he works out a work cycle using mesoscopic superconductors to carry out work, banking on the normal to superconducting transition. The challenges of the University of San Diego go back 20 years now. First ideas were about 1990, late 1990, and they have always focused on ones which are experimentally testable, at least facets, I should say, the underlying physics can be directly tested. So here's a compendium of them. Wherever you see a star indicates experiments have been done which corroborate the fundamental processes underlying the challenge. I was trained as a plasma physicist, so the first couple were in plasma physics. My undergraduates in chemistry, a chemical one was actually the first one I worked on. And then from there, these developed into various kinds of catalysts and solid-state devices. Many of the effects which are discussed in these particular challenges have been corroborated by other researchers in their own independent research, one of whom is Sam Miller at Sandia National Labs, corroborates some of the chemical research we've done. Lindsay Gordon corroborates some of the stuff I've proposed in terms of biology, and Jack Denier in terms of the gas laws. So from the University of San Diego, these are the summary of the challenges. Plasma 1, plasma 2, gravitational, chemical, solid state. Temperature range in which they operate. The plasma ones operate at high temperature where plasmas exist, typically about 1500 Kelvin. So this is an inhospitable regime. You have to work with exotic metals like tungsten and tantalum and molybdenum. Pressures have to be low. Power densities are minute. Commercial interest is virtually none. The experiments which were done on these corroborated the process. And in principle, had these plasmas been actually created at room temperature rather than at 1500 Kelvin, then in principle these could have been claimed to have been true second law violators. But because of the high temperature, having to run gas vacuum pumps, heating everything up, the amount of entropy I created was a quadrillion times more than I could have harvested from these processes. Chemical processes also have relatively high power densities, but generally will not be commercially interesting. I'd like to focus on the solid state challenges, which have enormous power densities in principle, greater than, in principle, 100 megawatts per cubic meter for these small devices. They're microscopic or to begin with, and they could have commercial interest. These can operate anywhere from the boiling point of liquid nitrogen up to about 1000 Kelvin. The plasma experiments were basically heating up a cavity to a couple thousand degrees, putting in disparate metals, and putting in an ionizable metal like, that could be surface ionized like potassium, and seeing whether the amount of current or the amount of ionization caused by these different materials was different. If so, it would generate a differential current, and the experimental evidence indicated that the differential current, which was measured between different types of metals, say tantalum versus hafnium, tantalum versus zirconium oxide, were indeed different, whereas if the metals were matched, you saw lesser or no difference, indicating that a second law or a differential current could be developed between two materials at thermal equilibrium, but the thermal equilibrium had to be very high in terms of temperature, so this is impractical. The chemical steady-state non-equilibria works in the following way. Let's say you have some diatomic hydrogen, H2, and you were to put diatomic hydrogen into an empty cavity which was made out of, let's say, surface type 2 all around, and you have a piston which has surface type 2 on one side and a small patch of a different surface type, let's say surface type 1 on the other. Now, just for argument's sake, let's say at a high temperature when diatomic hydrogen intersects and lands on the surface, if it lands on surface 2, it simply bounces off or stays on the surface for a while and leaves as diatomic hydrogen. And moreover, if monoatomic hydrogen lands on the surface, that skitters around, finds itself, forms diatomic hydrogen, and then leaves. On the other hand, surface 1, let's say, disassociates hydrogen. So when a hydrogen molecule comes on, it disassociates and comes off as two hydrogen atoms. It's straightforward to show that under these conditions at thermal equilibrium, if the molecules leave at thermal equilibrium from the surfaces, that there will be a net pressure over surface 1 relative to surface 2, and there will be a net pressure on this piston which can make it run. This would be a way of extracting work from the heat bath. This requires, though, that you have two different metals which have different propensities for dissociation of hydrogen. 10 years ago, I did experiments with molybdenum and tungsten at high temperature, around 2,000 to 3,000 Kelvin, in which I looked at the dissociation rate, the amount of dissociation rate of molecular hydrogen on tungsten versus molybdenum, and indeed, I saw distinct differences, enough to actually drive a small, low-power radiometer. But again, the experiments were done at high temperature and have no commercial interest and have generated no interest from the scientific community. Okay, which brings me to the last of the challenges which my colleagues and I have been working on for roughly better part of 10 years now, which deals with semiconductors. And these have the most possible commercial application, in my opinion, aside maybe from some gas cycles that have been proposed. Ken Rowan, who will speak next, will propose a gas cycle which could have very high power densities. So let's talk about silicon devices. Everything, all the semiconductor devices that you have at your disposal, all your iPods, on BlackBerries, computers, are all based on silicon, but special kind of silicon. Silicon which is doped. And when I say doped, that simply means that you have a silicon lattice which has a small impurity in it of, let's say, 1 part in 10,000, or 1 part in a million of something like phosphorus for N-doping, connected to another piece of silicon which might have what's called p-doping, which would have something like boron in it, in a very small concentration. When you put small amounts of impurity into silicon, you change its electrical conductivity and electrical properties enormously. So what could you imagine? Well, with N-type doping, you have a surplus or an excess of mobile electrons in this lattice. In the p-type, you have an excess of what are called positive holes. So you can imagine that if you have this N and p-type material joined, that some of the electrons would diffuse over into the p-type material and some of the holes would diffuse into the N-type material. Now, to give you an example of how that might be, let's say we were to take all the men in this room and put them on this half of the room and tie them with bungee cords to the wall, and put all the women on this side of the room and tie bungee cords on them to that wall. Now, men and women are naturally going to intermingle, so they will slowly interpenetrate across the boundary, but eventually will be arrested by the bungee cord, but there'll be energy stored in those bungee cords. And in this case, similar thing happens. The electrons go to this side, the holes migrate to this side, but because of the charge imbalance of positive and negative charges in the lattice, an electric field is formed which arrests further diffusion. This is well known. There is no argument about this. This is called the depletion region of a p-n diode, and the electric fields that are sustained inside of here are on the order of something like 10 to the 7th volts per meter. In other words, 10 million volts per meter. Enormous voltages. But the voltage drop is only about 0.5 to 1 volt. So fairly low voltage, very high electric fields. Now, imagine you took this p-n diode and bent it like a pretzel. Here we have it again, N-type built it into a horseshoe pattern, and a p-type similarly. Here we have the junction at the top where you have the diffusion of electrons and holes forming an electric field here. At the bottom side, though, I have left an open vacuum gap where no electrons or holes can diffuse. Well, it turns out that based on conservation of energy, Kirchhoff's loop rule, or Faraday's law from one of Maxwell's equations, it's easy to show that if you take an electron or a charge of any sort and move it around this loop, if it starts here and goes up a potential and then comes around this loop and comes back to where it started, it had better go down a certain potential drop as well somewhere else in this circuit. So if you have a potential drop of a volt here, you have to have a potential rise somewhere else. It can't be anywhere else in the bulk, because if you did, you'd have electric fields here which would cause currents. Therefore, it can't be in the bulk. It must be across the gap. So you can make an airtight analytic argument that in a p-n junction of this sort, across the vacuum gap, you should have a very large electric field. The voltage drop here has to be expressed as a voltage drop here in the opposite sense, and as a result, the electric field here can be quite intense. The electric field here is usually smeared out over a distance of about a micron or so. Down here, you can make it 100 times less if you wish by making this gap narrower, in which case you can make the electric field enormous. You can make it 10 or 100 times greater than it is in here. In doing so, you can store electrostatic potential energy in the electric field. Those of you who do physics or electrical engineering know that a capacitor does just this. A capacitor is a device which stores energy in charges, or if you wish, in electric field energy. So this is a capacitor which is charged, and is charged by thermal motion, and is charged forever. This is a thermally charged capacitor until you find some way maybe of exploiting that energy. This is a simulation done with advanced semiconductor software from the Bay Area, Silvaco International. They conducted a number of simulations for us. We did our own. Both our simulations agreed with each other. They did theirs in an unbiased way, and they found that indeed, when you make an N and P-type material and join them, you see electric fields up here, which are fairly weak, on the order of 10 to the 4th, 10 to the 5th volts per meter. But in this gap, you see enormously intense electric fields. One's on the order of 10 to the 7th volts per meter. So this thermal capacitor can be shown analytically, can be shown by numerical simulation, and there's a lot of corroborative evidence from the solid state community that it's already been measured experimentally as well. So imagine what you might be able to do. I'd like to imagine first a very simple device. Let's say we have something we'll call a hammer, which is a movable top of a capacitor, just a metallic plate hooked to a spring with spring constant K, hooked to a resistor, hooked to a power supply. Power supply comes up and is hooked to the bottom part of this metal, another metal plate across a vacuum gap, and this is called the anvil. Now you can imagine the following happening. This voltage power supply will charge up this side of the capacitor and this side of the capacitor, positive here, negative here, and you'll have an attraction of the top plate against the bottom plate. When they come together, the charges will annihilate each other instantaneously. The capacitor will discharge. But of course, it has, at that point, pulled on this spring, which will retract back the hammer. The hammer will recharge on the time scale set by the capacitance of these plates and the resistance of the resistor, what's called the RC time constant. Now, if the natural mechanical oscillation frequency of this hammer equals the time constant for the recharge, you can imagine the top plate charging up, being attracted down, touching, discharging, being pulled back, recharging, being pulled back, discharging, being pulled back, recharging, basically forever. This is called an electromechanical oscillator. These are very common in technology. In fact, if you have an old regular quartz wristwatch, this is an electromechanical oscillator. So these are well known. A student of mine and I built one of these things in the afternoon, during one afternoon with a high voltage power supply, and it worked like a charm. Not a problem at all. But let's translate this now. Let's translate this to a system in which, instead of having a power supply here creating the voltage, we have depletion regions between an N and P semiconductor creating the voltage. In this case, you have the same electric field across this hammer and anvil gap as you had here. And if these are thin springs, thin leaf cantilevers of silicon, they would take the place of this mechanical spring. And we've also devised ways of inserting resistances into these lines to vary the resistance. In doing so, you can make an electromechanical oscillator here, which is equivalent to the electromechanical oscillator here, the difference being this one is powered by the wall plug or by a coal burning plant, and this is powered by the p-n junction. You can work out work cycles for this and show that indeed you can make work cycles out of this cantilever device. We built prototypes about a year ago of a torsional version of this oscillator, which ran into problems during the fabrication process, so we decided to back up and look at two-dimensional versions of it. These are electron micrographs of silicon chips which we just had fabricated and finished last week, which incorporate various ideas which I just discussed. Here's a gap where you have p-type silicon here, n-type silicon here. We will be using Kelvin probes to measure the electric field in this gap to see whether indeed the intense electric fields that we predict are there. We have made cantilevers where we have N and p-type semiconductors offset by a very narrow gap, and we will measure whether, when we close this gap mechanically, whether we see the discharge we predict, and when we pull it back, that it recharges. If that happens, we are very close to making a full three-dimensional second law violator, in my opinion. We have apparatus built for tests of these. These are set up at Sandia National Labs, and we pursued probably in the next year or so. So the research status with regard to our second law work, we currently have second law diodes, two-dimensional diodes in hand, and we'll be testing them during the summer, and we have plans in process to build 3D torsional oscillators to test the hypothesis. So, in the end, what a number of researchers and I propose is that the second law, although it is now considered absolute, have a number of possible challenges that have been leveled against it which have received no response from the scientific community. The community is silent and has found no way to, how should I put it, refute these challenges. But we are now in the position where the burden of proof falls on us to do the experiment. Theorists do not make truth. Nature has its truth, which we have to discover. So again, as I said, the second law is inviolable until it is no longer. And it is our goal to change the rules of not only the second law's game, but the game of energy as is currently played in our society. Thank you. Questions? Peter?
Comment some more on the Maxwell Demon. I mean, you said the idea is no good because entropy is concerned. There are two versions of the entropy. One is information, and
Yes.
the other is the motion of particles.
Right.
It's not obvious to me that they are the same.
Right.
So could you comment on that? And also, would you say whether the work you're doing implicitly invalidates the Maxwell Demon argument?
Okay, sure. So let's back up. The Maxwell Demon, as proposed by Maxwell 140 years ago, was a thought experiment, which basically says, can you shepherd particles either by temperature or location to create pressure differentials? Okay, and the way Maxwell proposed it ended up making it a straw man argument, and the information theorists starting back in the 1960s began to realize when they were looking at computers that indeed, if you're going to have a computer, you have to do something with your excess information if you want to erase a bit. When you erase a bit, you have lost information, but that increases the entropy of the universe. So if you make a Maxwell Demon, in other words, a thinking one that records the position of molecules and keeps track of them in some sort of register, if it's going to do it in a cyclic way, then ultimately it has to go back and forget what the previous cycle. Otherwise, it's no longer a cyclic process. But in the very process of forgetting, in other words, erasing a bit of information, it creates a bit of entropy. And that apparently is what finally foils the Maxwell Demon. Unfortunately, many scientists have conflated thinking Maxwell Demons against ones which naturally arrange themselves, like the ones which have been explored over the last 20 years. So the Maxwell Demon, as it's currently understood, is basically a straw man because it incorporates the thinking creatures. Ours are Maxwell zombies. They don't think. Okay.
We actually have a fairly long time for questions because Daniel ended ahead of schedule. So before we go to the next question, I would like to make one comment, which is that I believe you gave a talk very similar to this one about 2 years ago, and I'm personally a bit disappointed that in terms of experimental progress, you seem to be in about the same place you were then.
Actually, that's not the case, York. We have built some silicon devices in the last 2 years, and as they say in science, it's all about time and money. Okay.
The question I had is that as those thin strips of silicon are moved or stressed on a cyclic basis,
yes,
you're going to get fatigue setting in, which is a part of the second law. You know, it takes energy to do that. But don't they finally fail?
Yeah,
and have you taken that into account?
Yes, we have. There are three main criterion by which these devices have to satisfy. First of all, you have to make a electromechanical silicon device that has an equivalence basically between the time constant, the electric time constant and the mechanical time constant, such that they coincide, such that you get this electromechanical resonance. The second one is that the amount of loss in the system, in other words, the amount of damping in the system from the springs, has to be below that. The mechanical losses have to be less than the energy gain during each cycle from the motion. And that requires very high Q, high quality factor springs, which is why we're using silicon crystal. You can make Qs of an order 100,000 with silicon. And that is also important. So we're going to have to work in a Q regime of around 1,000 or more. So that's certainly the case. But we're working in the linear regime where fatigue should not be a serious factor. And the third one has to do with stiction. We have to have enough pullback that it can overcome surface stiction. And we have found regimes in which all three of these can be satisfied mutually. And so as far as we know, there is no physical impediment to making one of these devices.
Over here.
Over here.
Suppose next year you violate the second law. Do you have any idea how you would correct it, restate it so it's not inviolable?
I think I did. Second, the entropy of the universe never decreases except when it does. It is. Well, the whole point is that the second law is an absolute statement. It says something that this is impossible. So what we're saying is that in certain cases it isn't. It's like saying pigs don't fly. Pigs don't fly unless you load them on a plane. Then they do. So it's a question of finding the regimes in which it is applicable. The second law in its current state is absolutely true. But if there are exceptions to it, then you have to throw it out as an absolute law. Well, I don't find that a good reason not to pursue my research. It's their problem, not mine. I mean, I'm simply testing this law, and there are enough theoretical arguments now, not just from me, but from a dozen other research groups, that indicate there are probably problems with it. Now think about it. The second law was discovered and was developed around the idea of steam engines 150 years ago. And what has happened since then? We have pushed the boundaries of temperature from nanokelvin up to a billion degrees in the laboratory. We have pushed the densities of materials up by implosion techniques by a factor of 100. We have discovered quantum mechanics. We have discovered superconductivity. We've discovered chaos theory, special relativity, general relativity, and it is the only law that I'm aware of that has not been updated in 200 years. And my belief is that it probably needs to be updated. And the updating is basically to say it is no longer absolute any more than the ideal gas law is absolute. The ideal gas law is an excellent, a very good approximation, but it is not absolute. It's a good approximation. I think I believe the second law will ultimately turn out to be a very good approximation, but not absolutely true.
Two more brief questions.
On the hammer-anvil contact point?
Yes.
What keeps that from just forming yet another diode, or sort of like a PIN diode with a little
it does.
vacuum layer?
Yes, it does.
But after the first contact, wouldn't there be no current?
No, what happens is there are two things happening. In fact, you could slow this thing down if you wished and actually stop it there and form a complete PN diode. It takes a certain amount of time for it to form. Okay, it takes 100 nanoseconds or longer if you have a resistive load on it. But when it touches and the charges begin to diffuse, the electric field decreases because now the electric field is extending over the depletion region. But recall that electrostatic pressure goes as epsilon naught, the permittivity of free space, divided by 2 times the electric field squared. It goes quadratically as the electric field. So when the contact is made, even if you do get the formation of an entire p-n junction, the electric field is dropped by a factor of 10, therefore the pressure is dropped by a factor of 100, and therefore the spring can retract it.
You mentioned background fluctuations briefly in one of your slides.
Yes.
Within limits, hasn't this already been a violation of the second law?
Not that I'm aware. The second law